Finding an exoplanet is like searching for a tiny needle in a cosmic haystack. The search relies on indirect evidence because these worlds are too small and faint to see directly. Now let us explore the two main methods, the radial velocity and the transit method. Both concepts exploit how a planet's gravity affects its host star. Consider a star and one planet orbiting around a common center of mass, the barycenter. Star does not stay perfectly still, instead it slowly orbits the barycenter. This subtle motion, the stellar wobble, is the key to the first technique. As the star moves toward us and away from us, the light it emits changes frequency. This is the Doppler shift, which stretches light to red and compresses it to blue. The radial velocity method measures this shift to calculate the star's speed toward or away from Earth. A planet with higher mass causes a more noticeable wobble, leading to a stronger Doppler signal. By contrast, a smaller, less massive planet produces a much fainter and harder to detect wobble. We can also determine the planet's orbit period from the time it takes the star to complete one wobble. This is why a star's light is a precise and continuous speedometer for astronomers. This method works best for large gas giant planets orbiting close to their stars. Now on the diagram we see the star's velocity plotted over time, forming a distinct sine wave. The height of the wave reveals the minimum mass of the exoplanet. The period of the wave directly gives the period of the exoplanet's orbit. However, the radial velocity method only gives the minimum mass because of our viewing angle. If the orbit is face-on to us, the star moves sideways, showing no measurable radial velocity shift. The wobble is strongest when the orbit is edge-on, maximizing the star's line of sight motion. Next we turn to the second major discovery technique, the transit method. This method requires the planet's orbit to be perfectly edge-on as viewed from Earth. A transit occurs when a planet crosses the face of its star, temporarily blocking a tiny fraction of light. The transit itself can last for hours, depending on the star and the planet's orbit. On the diagram, the star's brightness, the light curve, shows a characteristic dip during the transit. The depth of the light curve dip reveals the relative size of the planet compared to the star. A bigger planet will block more light, creating a deeper and easier to detect dip in brightness. The time between dips gives the orbit period, which helps calculate the orbital distance. This method, pioneered by missions like Kepler, is responsible for the majority of exoplanet discoveries. Transit photometry is extremely effective for finding smaller, potentially Earth-sized planets. Now we compare the two methods to see how they complement each other. Radial velocity can estimate the planet's mass, but it cannot measure its size. By contrast, the transit method determines a planet's size, but it cannot measure its mass. The ideal discovery uses both methods on the same exoplanet to find both its mass and its radius. Knowing both size and mass allows scientists to calculate the planet's density. A low density suggests a gas or ice giant, while a high density suggests a rocky terrestrial world. From above, we see the Kepler Space Telescope's orbit following Earth as it continuously observes one small star field. Kepler used a single, massive camera to monitor the brightness of over 0 stars simultaneously. The data produced a precise light curve for each star, revealing minute dips caused by transits. Kepler's revolutionary success proved that exoplanets, including small rocky ones, are common in the galaxy. The TESS mission, the Transiting Exoplanet Survey satellite, uses the same transit method. TESS observes almost the entire sky, focusing on brighter, closer stars than Kepler did. This allows for easier follow-up observations by the most powerful ground-based telescopes. The bright nearby stars TESS focuses on are ideal targets for atmospheric studies by the James Webb Space Telescope. Now let us look inside the TESS spacecraft on this cutaway view to understand its simple design. TESS uses 4 simple but powerful wide-field cameras to cover huge segments of the sky. The spacecraft does not use reaction wheels. Instead, it maintains pointing stability using magnetic torquers. TESS orbits Earth at a high altitude far beyond the Moon in a unique and highly stable resonance. This unique orbit provides nearly continuous observation time, minimizing the Earth's disruption. Because the orbital period is half the Moon's, TESS makes one orbit for every 2 Moon orbits. The TESS mission continues to find thousands of promising exoplanet candidates around nearby stars. Many of these candidates are confirmed by ground-based radial velocity observations. The combination of TESS and radial velocity is the most effective way to characterize a new world. This combined approach allows astronomers to calculate the world's density with high precision. The ultimate goal is to find rocky worlds similar to Earth orbiting in their star's habitable zone. The habitable zone is the orbital distance where liquid water can exist on the planet's surface. TESS discovered the 7 Earth-sized exoplanets orbiting the nearby TRAPPIST-1 star system. The TRAPPIST-1 system is a prime example where 3 of the 7 planets lie in the habitable zone. Now we will look at how the data from these missions are verified and studied further. The first step is to rule out false positives, which are common with the transit method. A common false positive is a background star that is temporarily eclipsed by a foreground star. Another possibility is a huge planet orbiting a very small star, mimicking a smaller planet orbiting a larger star. Ground-based telescopes perform immediate follow-up to confirm the signal is from the target star. This confirmation process uses radial velocity to verify the planetary mass is consistent with the transit size. Once confirmed, the exoplanet gets a designation and is added to the official catalogue. The catalogue now contains thousands of worlds with extremely diverse properties. This is why the discoveries range from hot Jupiters to super-Earths and mini-Neptunes. Super-Earths are terrestrial planets up to 10 times the mass of Earth. Mini-Neptunes are gaseous worlds smaller than Neptune, a class not found in our solar system. The diversity of exoplanets shows that our own solar system is not a perfect template. This insight is one of the most profound scientific revolutions of the last 30 years. Now we examine the next frontier, studying exoplanet atmospheres with the James Webb Space Telescope. When an exoplanet transits its star, a tiny amount of starlight passes through its atmosphere. Different gases in the atmosphere absorb specific wavelengths of the starlight. The James Webb Space Telescope, with its infrared sensitivity, can detect these unique absorption signatures. This technique is called transmission spectroscopy, and it is a major focus for future discovery. Detecting molecules like water vapor, carbon dioxide, and methane can reveal the atmosphere's composition. Finding a combination of gases that is out of equilibrium could signal the presence of life. For example, large amounts of both oxygen and methane together is difficult to explain without biology. The ability to study these atmospheres is the direct payoff of the Wobble and transit methods. Let us look at an example. The hot Jupiter WASP-96ab, a primary target for Webb. WASP-96 orbits extremely close to its star, completing one orbit in just 3.5 days. Even so, Webb has precisely measured water vapor and other molecules in its superheated atmosphere. This demonstrated the telescope's power to analyze the chemistry of distant worlds with precision. Webb is also capable of directly imaging large, distant exoplanets by blocking the light from their star. This direct imaging method uses a device called a coronagraph to mask the star's glare. Direct imaging is currently limited to very large, young and hot planets orbiting far from their stars. Now we look at the next big missions that will continue the search for Earth-like worlds. The Plato mission by ESA will search for transiting planets around Sun-like stars. Plato will focus on planets orbiting in the habitable zone with the goal of detecting planets like Earth. Its design uses 26 smaller cameras, allowing it to study a huge area of the sky. Plato will provide better precision and coverage of bright stars than the TESS mission. The future of exoplanet discovery is a combination of powerful space telescopes and ground-based observatories. From above, the next generation of extremely large telescopes are now under construction. These ground-based telescopes will use adaptive optics to sharpen starlight through Earth's turbulent atmosphere. The giant Magellan telescope, for example, will use 7 large mirror segments to achieve a massive light-collecting area. The sheer size and precision will enable new radial velocity measurements of unprecedented accuracy. This improved accuracy will allow the detection of even smaller, less massive exoplanets. The most distant goal remains detecting biosignatures, chemical hints of life, on a world like our own. This requires both the transit method for size and the radial velocity method for mass. Knowing both gives the planetary density, which is the crucial link to finding rocky worlds. Finding a rocky planet with liquid water in the habitable zone is the first necessary step. The search started with the slight stellar wobble and the subtle dimming of starlight. This is why the simple physics of gravity and light are revealing the structure of the cosmos. Recap. The radial velocity method uses the Doppler shift to find the star's tiny wobble. This wobble is the gravitational tug of a planet that is too faint to be seen. By contrast, the transit method observes the tiny dip in starlight as a planet passes in front. This dip directly gives the size and orbital period of the distant exoplanet. Both methods together, mass from wobble and size from transit, provide the key planetary density. Density is what determines if a world is gaseous, icy, or rocky like Earth. The Kepler and TESS missions have proven that the universe is teeming with diverse exoplanets. Webb is now taking the next step, analyzing the chemical composition of their thin atmospheres. The goal is to find one world that is truly similar to Earth, one that harbors life. The techniques are simple, yet the result is a revolution in how we see our place in the galaxy. So the next time you look at the stars, know that thousands of worlds are being discovered right now. The cosmos is vast and dynamic, but the simple laws of physics reveal its hidden planets. The search continues with new missions, each building on the discoveries of the last. We are closer than ever to answering the ancient question, are we alone? This is the power of science, turning a faint wobble and a small dip into the knowledge of new worlds.